My name is Nakang Teddy, Computer Science here at Macquarie University, and I'm going to take you through part of our project. Another topic, strategies, personal legislation for fraudulent gas and power consumption detection. So under our topic, we have some keywords, have anomaly detection, which is to do with detecting unusual occurrences in data, deep learning, that is use of neural networks to solve complex problems, and have fraud detection, which is detecting fraudulent activities like we're talking about, then machine learning to teach machines how to do tasks without explicitly telling them how to do them. Then multi-strategy learning, use of different techniques to train these models. Then power fraud, that customers deliberately steal these resources we're talking about. Then personal legislation, for it is to do with training a large teacher model and then distilling its knowledge to a smaller student model and applying sparsity to obtain a lightweight model. So these are some of the contents that we're going to present to you, and they are listed there. And then about the background, we are looking at fraud in gas and power consumption, and the concern is that it causes financial losses to these utility companies and sometimes inaccurate billing to the customers that use the resources, and even the traditional methods that struggle with this imbalanced data to scale their models in detecting fraud in gas and power. So that brings in the need for our project, which is multi-strategy personal legislation for fraudulent gas and power consumption detection. Our system integrates three teacher models, that is random forest, XGBoost, and LightGBM, and then involves knowledge distillation, where we distill knowledge of this individual after averaging the individual prediction probabilities of these teacher models, and then distill to an artificial neural network, and then apply sparsity to it, obtain a lightweight model. So these are some of the related works. It's recent work of 2024. The table includes the paper references, the models that they did, the contributions and the limitations they encountered. So the problem is basically fraud activities, for example, meter tampering, illegal connections, and energy theft that lead to financial losses to the utility companies that supply power and gas. Then computational problems that we're trying to address are basically high data imbalance, and with that, the fraud detection data sets are usually highly imbalanced with very few fraud cases compared to the non-fraud cases. So that leads to the model being biased towards the majority class. So we applied resampling technique. We applied hybrid resampling technique, and we used SMOT, that is synthetic minority oversampling technique, and then near miss, that is undersampling of the majority class, ensuring better model sensitivity and to fraud cases. Then we also looked at scalability issues, where we are training several models, and because we are training several models, it would be computationally expensive for a large data set like the one we used. So we solved that by using this distillation. So we distilled knowledge from multiple teachers into one sparse neural network student model, and then also looked at model size and deployment efficiency as a computational problem. And for it is because that even this standard artificial neural network can be large and inefficient for real-world deployment. So after training, we applied specification techniques, that is pruning, and made it a lightweight model, faster for deployment via an API, and that is with the web app that we used. Then some of the research questions we're asking ourselves are there, that if a multi-strategy personally can improve detection of this fraudulent gas in power and consumption, if there is a technique that can effectively address this imbalance problem of the data, and then we wanted to assess to ask ourselves if these hybrid resampling techniques can affect the performance of the sparse model. Then our research objectives included developing a multi-strategy personal legislation to improve fraud detection accuracy in gas and power. Then we also wanted to implement and evaluate techniques for handling the highly imbalanced data set. And then I wanted to assess the computational efficiency of our proposed model or to the traditional ways of detecting fraud. And then, as our research contributions, things we did, we basically developed a multi-strategy spatial legislation model to enhance fraud detection, accuracy, gas and power, but maintained computational efficiency. Also implemented and evaluated a hybrid resampling technique, and it really worked well because we were able to obtain balanced data after that. And then we also assessed the computational efficiency of our sparse model uh, by comparing it to the traditional machine learning fraud detection techniques. And then the methodology. So this illustration here shows the overall methodology of the processes we went through as we continued to develop and improve the model. And then this is basically the architecture of the model that was deployed, where we had raw data, we did data processing and cleaned it. We then trained 3 individual teacher models, then evaluated them. We performed ensemble learning, but then did not use the voting classifier results for knowledge distillation because for knowledge distillation and deployment because it was misclassifying the fraud classes on deployment. So we went on and averaged the prediction probabilities of these 3 individual models and then obtained soft labels which were used to train an artificial neural network, after which we applied spaCy to obtain a lightweight model and then created an API and then and a web app, then deployed a production model of a render. And then the data set that we worked with was a large data set that we sourced from Steg. It included client information and billing history. It has very many entries. It was between 25 to 2019. It had different features which included client information like client ID, district, region, and then target values which indicated the fraud and non-fraud cases. So we went on and did an explorated data analysis on the data after cleaning it, and we were able to come up with these visualizations to help us fully understand the data that we were working with, and we could see that we had an imbalanced data set with very many fraud cases and with very few fraud cases and many non-fraud cases. We're able to see the distribution by region, by district, and even the tariff types. Yeah, my pleasure.
Hello, my name is Namatahola Mwenesha, and continuing from where my friends stopped. So here in slide 10, we did perform an exploratory data analysis to understand the data set structure, distribution of features, and to confirm the presence of the severe class imbalance, which did inform our resampling strategy, where we applied what near miss for highly imbalanced data sets. And so here in slide 11, we eventually the results and the discussions from the models here we trained 10 models: the logistic regression, ANN, isolation forest, decision tree, naive Bayes, as they are listed here, and we did consider precision for the class 0, which is the non-fraudulent, and class 1, where we have the fraudulent consumption, which this is cyber data. And so we also looked at the accuracy, but our major focus was measured in the precision of class 0 and class 1. So we evaluated multiple models, and from here we were able to discover that our multi-strategy knowledge distillation model showed superior performance compared to the other traditional approaches of, well, just train simpler models. But then so here. So here it achieved a higher accuracy while keeping computational costs low, and which is very critical for real world deployment. And so in slide 14, here we went on to do the explainable AI techniques. This is a sharp this is a sharp plot for the best model which deployed, which was the first ANN. And from here, we understand why the model made specific decisions, especially for the worst performing cases. And this insight majorly helps us to improve the model's reliability and transparency when it is deployed in real world cases. And so this is our hosted. This is our hosted version of the model, and this is what it looks like. So here you enter the features, you enter the district, the client ID, the client category, the region, the creation date. You do enter the tariff type, the counter number, the counter code, the confirmation type, and then the counter type, which is either electricity or gas. And then you go on to click predict. And when it returns fraud, like here, we know that that consumer is involved in fraudulent consumption. When it returns non-fraud, we know that that consumer is not involved in fraudulent consumption. And then for the IP identified, we did develop a very unique workflow, which is very suitable for patenting, copyrighted code and documentation. And we do believe our proprietary methods are protected as trade secrets, providing a foundation for commercialization, which we plan to do later on. So here, in conclusion, we were able to success this. For conclusion and limitation, conclusively, we were able to successfully create a robust fraud detection system that leverages strategy learning, past learning, and knowledge distillation. We were able to address the imbalancement of our data set using SMOT and near miss, which were techniques we got like from a research paper, the research paper that created that data set. Like it was a research paper which was published by the company that created the data set. So I experienced like some challenges, and we had to go and do deep research on how to handle this data set, and then that's where we came up with SMOT and near miss. And however, but we still have some challenges in real-time deployment and handling extreme class imbalance. So what we plan to do in the next steps majorly include pursuing commercialization, integrating real-time alerts, deploying the system in utility companies like ADCL, and continuously monitoring our model performance and adapting the system in other sectors like water communications fraud detection. We want to like scale it so that it goes to other utilities as well. And finally, so in the acknowledgement, we would really want to thank our supervisor, Mr. Galiwango Marvin, for his guidance, continuous guidance and mentorship. We would also love to appreciate the Unipod office for supporting this project, this work with resourcing, training. And then we also love to thank ourselves for not giving up and for working continuously, and everyone who contributed directly or indirectly to the success of this project. Thank you so much.